Hello everyone, I'm Norman Wahlberger, and we're here at the University of New South Wales. So last time we were sort of introducing curvature via study of a parabola. And today we want to continue with that so that we're in a position of defining the curvature for general algebraic curves in the plane, and that we're able to compute evolutes of actually quite a lot of examples. All right, so let me summarize the theorem that we proved last time. We did some calculations for a parabola in somewhat general position, and the theorem is that the parabola, say P, with vertex 0, 0, and focus, say F, the point F, G, is, so the equation is gx minus fy squared equals 4f squared plus g squared times fx plus gy. And if g is not equal to 0, then locally at or near the origin, up to quadratic terms, it equals the function y equals alpha x plus beta x squared, where we determined that alpha was minus f over g and beta was f squared plus g squared over 4g cubed. And given alpha and beta, on the other hand, we find that f is minus alpha times 1 plus alpha squared all over 4 beta, and g is just 1 plus alpha squared on 4 beta. All right, so the picture we have is we're in the plane. We have some focus point, FG, and then we have corresponding perpendicular tangent line, and then the parabola P. And the directrix will be an equal amount out this way here. There will be the directrix L. All right, so basically, given the point FG and the knowledge that the vertex is at the origin, then we can write down the equation of the parabola. We can determine that locally it's a function whose first few terms in a Taylor expansion is alpha x plus beta x squared. So we're ignoring higher powers of x like we do with the Lagrange approach. And we have this nice duality between the alphas and betas and the f's and g's. We can calculate the alphas and betas from the f and g's. On the other hand, we can calculate the f's and g's from the alphas and the betas. Okay, now what we want to do is we want to extend this to the general conic through the origin. We want to extend to a general conic that's passing through the origin. And let's call it, say, Z, this conic. And it will have, we'll assume it has the form Lx plus my. Those are the linear terms. And then the quadratic terms will be nx squared plus 2pxy plus qy squared equals 0. Okay, so it just doesn't have a constant term. That guarantees that it goes through the origin. That's a general conic passing through the origin. We'll note that the tangent line is just the linear part, so it's the line Lx plus my equals 0. And we'll also note that the quadratic part of the conic, so the quadratic part has matrix, because we like to represent quadratic forms with matrices. So we could represent that with the matrix n, q, and p's on the off-diagonal elements. All right, so what's our strategy going to be? Well, our strategy is that we've got now a general conic, and I'm going to maybe draw it on the same picture. Okay, so maybe the general conic is perhaps maybe it's an ellipse. Okay, something like that. And it's also got some tangent line. And what we're interested in doing is finding the normal parabola that's exactly lined up with this particular conic. Has the same tangent line, and quadratically near the 0 looks exactly the same as the given conic z. So basically we want to find, given the z, what would be the focus, f, for the parabola which approximates the conic at that point. But the parabola is such that its axis is directly perpendicular to the tangent line at that point. That's the vertex for that parabola. All right, our strategy to do that is to go via a function. So our strategy is to, well, first find the function y equals alpha x plus beta x squared, which approximates this conic. And then once we have that, we can use this formula here to immediately write down the parabola that corresponds to that function. So how are we going to find the function that agrees with this parabola? Well, it means that it has to satisfy the parabola up to quadratic terms. So we have to plug in and see what alpha and beta have to be in terms of L, M, N, P, and Q. So let's do that. So we'll plug in, and we'll get L times x plus m times y, which is going to be alpha x plus beta x squared. And then plus nx squared plus 2px times alpha x plus beta x squared. And plus q times alpha x plus beta x squared, all squared, should equal 0. I might leave this down here. Okay, so how are we going to find alpha and beta? Well, we'll look at the x terms on both sides of the equation. There's only this x term and the m alpha x term. All the other terms involve x squareds or higher powers. So there's an L plus m alpha, and that better be 0, which is the coefficient of x on the right-hand side. And then in terms of the coefficient of x squared, where do we get x squared? First one will be m times beta. and then plus n, then plus 2p alpha, and finally an x squared coming from when we square this term, we're going to get a q times alpha squared, plus q times alpha squared. So those are all the x squareds that appear in that expression, and we'll set them to equal to 0. And we're ignoring all cubic terms and higher powers of x, so these are the relevant equations that we need. And now we can write down what alpha and beta are. So the first equation tells us that alpha equals minus L over m. That's good. And let's see, the second equation tells us that beta equals, well, minus n plus 2p alpha plus q alpha squared all over the coefficient m. But then we can replace the alpha with a minus lm, a minus L over m. So there'll be a minus L over m here and a minus L over m squared. So that will give us then that beta equals, well, we'll take that numerator and we'll multiply out the denominator of m squared, which is here. So we'll multiply all that out by m squared to give us minus nm squared. Probably need to go over here. Nm squared. And then there'll be a minus sign here. So minus 2p, and then there's an L and an m. And plus q m squared. All of that divided by the m, and then the m squared that we're multiplying through by for a total of m cubed. Exactly. nm squared minus 2pm lm. We're putting an L over m here, so that last one should be an L squared. Thanks. All right, and now knowing what alpha and beta are, we can use these formulas down here to write down what the corresponding foci coordinates must be, the f and the g. So therefore, the focus fg of the associated normal parabola, by that I mean vertex at the identity, or at the origin, will be, okay, so the first one is f. So f will be minus alpha, 1 plus alpha squared on 4 beta. Okay, and alpha is supposed to be minus L on m. So what do we get? Well, there's going to be an L. There's going to be a minus sign in the front, so I'll put that there. And then there'll be an L, and there'll be an L squared plus m squared. And then in the denominator, there will be a 4. Maybe I'll put the 4 here, and I'll write this term here, nm squared minus 2plm plus ql squared. Okay, that's all in brackets. All right, so let's see why that's true. So alpha is minus L over m. So imagine L over m all squared. So there's an L squared over an m squared. So if we multiply through by an m squared, we're going to have an L squared plus m squared appearing there. And over here there will also be an L over m with a minus sign. So that will cancel with that one. And then to get rid of that, we should multiply through by m cubed. Okay, when we're inverting beta on the other side, down beta's this one here, so when we flip it upside down, there's an m cubed up on the top, which cancels with the m cubes that we just were introducing there. And we extend this minus sign, which is out front here, will come out here. And there'll still be a 4. And this term here is just exactly this term here that appears there. We don't need this anymore. So that's the formula for F. And the formula for G will be, well, it's going to be a lot the same. The formula is 1 plus alpha squared over 4 beta, so much the same. 1 plus alpha squared over 4 beta. And that's going to be minus m over 4 times the same quantity, L squared plus m squared over nm squared minus 2plm plus ql squared. All right, so this little ratio appears in both places. So if we maybe give it a name, let's call it delta, the ratio L squared plus m squared over this quantity m squared minus 2p lm plus ql squared. Then we could somewhat more succinctly write F and G as so with that notation, F would be minus L over 4 times delta, and G would be minus M over 4 times delta. Okay, so in terms of L, M, and N, and P and Q, L, M, N, P, and Q, the normal parabola is, okay, its expression is gx minus fy all squared equals 4 f squared plus g squared times fx plus gy. So if we replace g and f with these expressions involving L and M's and these other variables N, P, and Q, then what's going to happen? So this G is going to be replaced with an M, minus M, and a delta over 4. And then F will be replaced with a minus L times a delta over 4. There will be lots of delta over 4s. So there will be a delta over 4 in each factor here, and that will come out as a delta over 4 squared. And on this side here, there will also be delta over 4s. There will be 2 of them in this factor, and 1 of them coming out from this factor. So there will be 3 delta over 4s on this side, and 2 delta over 4s on this side coming out. And then what we're going to have left is Lx minus my squared equals, maybe I'll put the, it's actually minus delta over 4 that's appearing out. So that's the single factor that will be left. And then there'll be times 4 L squared plus M squared times Lx plus My. As a result of replacing the F's and G's with these expressions here, bringing the minus delta over 4's out, there's only one of them right there. And here's delta back here, so it's L squared plus M squared. And it has this denominator down here, which we may as well clear the fractions. So we can write it as altogether nm squared minus 2plm plus ql squared times lx minus my squared. And since there's a minus sign here, we might bring the other stuff to the other side. So then there'll be plus. There'll be L squared plus M squared. There'll be 2 of them because one was there and the other one comes from the numerator of delta. Times Lx plus My. And all of that has to be set equal to 0 if we bring this all to the other side. Okay, and we see that it's really in the same kind of form as the parabolas that we were considering last lecture, with a sort of cross product term squared, a dot product term on this side, and then some numbers that depend on the 5 coefficients L, M, N, P, and Q. Okay, so as a special case or an application of this, let's have a look at a very special conic related to F and G, and that's a circle. So the theorem is that the circle, let's call it C, C, centered at 2F and 2G through the origin, agrees up to degree 2 terms at the origin with the parabola, well, with a normal parabola with focus FG and vertex 0, 0. All right, so the proof. Well, the circle C has equation what? It's going through 2F, 2G, so its equation is x minus 2F squared plus y minus 2G squared, and it also goes to the origin, so its quadrants is 2F squared plus 2G squared. And that becomes 4fx plus 4gy minus x squared minus y squared equals 0. If I write it in the same standard form as I did for the general conic. So this is a situation where this 4f is playing the role of our L, the 4g is playing the role of the M, the minus 1 is the P, no, not the P, the N. There's a 0 for a P, and there's a minus 1 for a Q in our notation of the general conic. So what is the corresponding alphas and betas for this circle? So the circle is then approximated at 0, 0 by y equals alpha x plus beta x squared, where, well, the alphas and betas are just the same ones that we just computed for the general case, but with these specific values. Okay, so I'll remind you that the values were, alpha was minus L over M, so that's going to be minus this over this, that's just going to be minus F over G. And the beta expression was minus nm squared minus 2plm plus ql squared all over m cubed. Okay, what's that going to be? Well, so n is minus 1. The m is 4g. So we're going to have a 4g squared. The p is 0. The q is minus 1. So there's another minus times minus makes plus. And the l is the 4f. So we're going to have plus 4f all squared. And on the bottom we have m cubed. M is 4g. So we have 4g all cubed. for a total of g squared, all right, f squared plus g squared all over 4g cubed. So these two values, these are the same values that we got for the parabola whose focus was FG. These are the same values as for the parabola, the normal parabola, with focus F and G. So what's this telling us? It's telling us that if we have a parabola with a focus at FG, with a vertex at the origin, and we want to draw that parabola, maybe it's not so easy, but we can do a pretty good job by looking at the point 2F, 2G, and drawing the circle centered at that point, let's call it C, and that was F, through the origin. So we just draw this circle. It's supposed to be a circle centered at C, passing through the origin. And then what we've just shown is that close to the origin, that's a pretty good graph of the parabola whose focus is this point. All right, so this motivates us to define the quadrature or the curvature in terms of the curvature of this circle. And so we're going to make a couple of definitions. We're actually going to start not with the curvature itself, but rather the quadrants of this circle. So the quadrants of this circle is, let's say Q equals, well, it's going to be 4 times F squared plus G squared. The quadrants of curvature, of, well, let's give these things some names. So this circle, okay, let's call it C, maybe S, okay? The circle will be S, and the parabola, maybe I'll draw it in red, so the parabola whose focus is there is, okay, it's going to be pretty close to being this circle. Say in red there, let's call it P. And let's also consider another conic, a general conic, which is touching the origin in the same way as the parabola is. Like that general conic that we called Z previously. And so I'll just sort of draw it like this. Okay, so there might be Z. Okay, so we're going to define the quadrants of curvature of all three of these things, because at the origin they're all really the same, of S and P and Z, all three of them, to be, or the quadrants of curvature of this is by definition, and we're going to give it the name capital R. So I like to give capitals for sort of quadratic things. R will be just I'm calling it Q here, but I'm going to change notation, call it R. So 4 times F squared plus G squared. That's obviously this quadrants here, because that's the quadrants between this point and the origin. Right. And since these all touch, we're going to assign that same number to not just the circle, but also to the normal parabola and to the general conic that matches up with them. We're going to give them all this quadrants of curvature R, which is 4F squared plus G squared. And then some closely related definitions. So, definition. The quadratic curvature. Maybe I'll put a little hyphen in there, make sure that we're aware that it's something a little bit different from the usual curvature. And we're going to denote it by capital K, and it's by definition 1 over capital R. Well, it's going to be 1 over 4f squared plus g squared. And another definition, the radius of curvature will be little r, and that will be the square root of capital R. Dreaded square root. Painful, isn't it? Okay, but it's still an important notion. The square root of r, so that'll just be 2 times the square root of f squared plus g squared. And finally, the curvature will be k, little k, which is the square root of capital K. And that will be 1 over 2 square root of f squared plus g squared. All right, so classically, the curvature has played the main role. Historically, the radius of curvature and the curvature are the main objects of interest. But there's a good case to be made that these quadratic analogs are, in many situations, more algebraically pleasant, and you can sort of get at them in a nicer way. And because they're algebraic, we can actually define them over a general field. This discussion was a discussion that was completely algebraic, so it actually makes sense over a general field. All the equations, just algebraic. So we could be working over a finite field, or maybe the complex numbers. But there, taking square roots is more problematic. So these concepts don't really work so well for those other fields.